Welcome everyone to our OpenSim webinar. My name is Jen Hicks. I'm the Associate Director of the National Center for Simulation and Rehab Research that develops and supports OpenSim, and I'll be serving as the moderator today. I'm pleased to welcome today's presenter, Chris Dembia, who's joining us from Stanford University, and he'll be presenting on automating OpenSim workflows, an intro to the OpenSim API in Matlab. Next slide. So OpenSim is a freely available software package that allows you to visualize musculoskeletal structures and simulate the movements of humans and animals. The first goal of our webinar series is to showcase cutting-edge research that's being performed with OpenSim, as well as to enable our community to better use the software and to have a platform to communicate and collaborate with each other. Next slide. Before we get started, a few reminders about the format of the webinar. So we definitely want to take your questions. We'll do those at the end of the webinar in the Q&A panel. So for this webinar, we're also going to have a separate room afterwards if you want to try out the demo that Chris is talking about. So we'll take some general questions at the end of the webinar, and then if you have specific questions about the demo and want to try it out, then we'll take those in the separate Zoom room after the webinar. Next slide. So now I'd like to go ahead and introduce our speaker so we can go ahead and get started today. So Chris Dembia received his PhD recently working at Stanford's Neuromuscular Biomechanics Lab, where he collaborated with Nick Bianco to create state-of-the-art tools for analyzing and predicting human movements. This work resulted in the OpenSim MoCo project, which has had a swift uptake in the community. Chris is an OpenSim expert and also a key contributor to the development and support and community building for the software. So we're excited to have Chris speak today. And with that, I'll go ahead and let you get started.
Thanks, Jen, for the introduction. All right, good morning, everyone. Newcomers to OpenSim are most familiar with OpenSim's graphical user interface, or GUI. With the GUI, users can edit models, visualize models, and conduct the standard pipeline of scaling a model, performing inverse kinematics, then using computed muscle control to estimate muscle activity. However, suppose you're conducting a simulation study on running mechanics across 10 subjects. Conducting your simulations for all of these subjects through the GUI would be pretty tedious, and so for this reason, we provide the OpenSim API, which is a way to automate your OpenSim workflows. API stands for Application Programming Interface. It's the set of functions that OpenSim provides that an application, like the GUI, can use to perform operations like building a model or running a forward simulation. The OpenSim API provides functionality also that's beyond what's accessible in the GUI. The API is available through Matlab, Python, and C++. The API basically means using OpenSim as a software library. Many users have created their own applications using the OpenSim API, such as the Cinemas toolkit for simulations that depend on EMG data. Learning OpenSim's API is the first step towards expanding what you can accomplish with OpenSim. So what can you do with the OpenSim API? Here are some of the most common tasks. You can programmatically build a model, which is often more convenient than building a model through XML editing. You can conduct a forward simulation of a model. You can analyze an existing simulation. You can load existing models and modify them to suit your own needs. You can load and modify motion capture data. Lastly, you can build custom model components, such as custom muscles or joint types. Today, I'll show a glimpse of the first 4 tasks. We'll work with a very simple model, a point mass, m, with one translational degree of freedom, x, with an applied force, F. We'll build this model from scratch, using a controller to specify that the applied force F is a sinusoidal function of time. Then we'll simulate the model and visualize the simulation directly in Matlab. Next, we'll analyze our simulation by computing the final position of the point mass and computing joint reaction loads. Lastly, I'll show how you can load this model from an XML file and modify its mass properties. The code I'll show on my slides is available at the link shown here, tinyurl.com/OpenSim API. I encourage you to not bother with running the code during the webinar. If you're interested in trying the code yourself, join us for virtual office hours afterwards. Our first task with the API is to create a model. You can think of modeling as having two steps. On the left, a researcher makes decisions about what aspects of the real-life system are important and assembles OpenSim joints, bodies, and muscles accordingly. On the right, OpenSim takes this conceptual model and assembles a system of equations internally. A benefit of using OpenSim is that you don't have to write any equations in motion yourself. You can focus on the more interesting task of capturing the relevant behavior of your system. A model is composed of components, including bodies, joints, kinematic constraints, forces, which includes muscles, and controllers. On the right is a specific example. A lower limb model would have a femur body, a hip joint, a constraint for patella motion, a soleus muscle, etc. This layout should be familiar to you if you've used an OpenSim XML file, perhaps viewing it in a text editor. In our point mass example today, we'll add 4 components to our model through Matlab. We'll add a body, a slider joint, a coordinate actuator to apply forces to the point mass, and a prescribed controller to set the control signal that we feed to the actuator. So let's begin. Here I've started with an empty Matlab script. The first line we write when using OpenSim in Matlab is to importing the OpenSim libraries, import org.opensim.modeling. Next, we create an empty model. If you're familiar with object-oriented programming, this line invokes the constructor of the model class to create an instance of the model class, and we store that instance in a variable named model with lowercase m. I'll give a quick intro to object-oriented programming for those who are not familiar. There are 3 key concepts: classes, instances, and inheritance. A class, or a type, is a category that groups together both data and behavior, or functions, that you can perform on those data. The body class contains data for its mass and functions to obtain and set that mass, get mass and set mass. You cannot use a class directly, however. You need to first create an instance or object of that class. For example, OpenSim models contain many instances of the body class, such as femur and tibia. You create an instance of a class with a special function called a constructor, which looks like using the name of the class as a function with parentheses. Once you have an instance of a class, you can then invoke functions on that class, like femur.getMass. If you have an instance of an OpenSim class and you want to know what type of object it is, you can use MATLAB's class function, as shown below. By convention, names of classes start with a capital letter, like capital B for body, and names of instances or objects start with a lowercase letter, shown here with femur and tibia. The last key concept is that classes can form a hierarchy. For example, the slider joint is a class that inherits from the joint class. A slider joint is a more specific type of joint. We call joint a base class and slider joint a derived class. An instance of the slider joint class provides all the functions of its base class and might provide additional functions that the base class does not provide. All of the components in a model are implemented as classes in C++. There's a base class called model component that provides basic functionality. The body class is derived from the model component class, as are the rest of these components. So let's revisit this line I showed earlier. This line invokes the constructor of the model class on the right to create an instance of the model class, and we store that instance in the model variable on the left. An empty model contains only one component, the ground body. We'll use this later. Now that we've created an empty model, we're ready to add a body to the model to represent the point mass. Here, I've used the constructor for the body class to create a new body. This constructor takes 4 arguments: the name of the body, the mass of the body, its mass center location, which we're specifying to be the origin of the body, and its inertia matrix. We've stored the body in a variable named body with a lowercase b. In OpenSim, bodies do not come with any visualization. To see the body, we add visual geometry to it. As shown in this image, OpenSim provides boxes, cylinders, ellipsoids, and spheres. You can also use mesh files. The body class has a function, attachGeometry, that takes an OpenSim geometry object. In this case, we're attaching sphere geometry. The constructor to sphere takes the radius of the sphere, which we've specified as 0.1 meters. We're now done configuring our body, so now we can add it to the model. The model has a function, addBody, that takes the body as an argument. Now the body is part of the model. How did I know that body has a function, attachGeometry? The two most useful ways for you to discover what functionality is available for a given class are Matlab's function methodsView, which shows all functions provided by a given class, and the Doxygen documentation website. For example, if I run the following in the Matlab command window, I'll get this pop-up. This window lists all functions provided by the body class, along with the arguments required by the functions, and what the functions return. This window doesn't provide much documentation other than the function signature. If I need more detail, I go to the Doxygen website. The Doxygen website is an API reference. It's not meant to be read linearly. It's more like an encyclopedia than a manual. The typical way to use this site is to search for the class you want using the search bar in the upper right, then scroll to see which functions are available. Many of the functions in a class may be in a base class. For example, the body class derives from the base class frame, and attachGeometry is provided by the frame base class. Moving along, we'll now add a slider joint to the model. A joint specifies how two bodies can move with respect to one another. OpenSim contains a library of different joint types. Here's a ball joint that permits 3 rotational degrees of freedom, a pin joint that allows 1 rotational degree of freedom, a slider joint that allows 1 translational degree of freedom, and OpenSim also allows specifying custom joints that permit arbitrary motion between two bodies. In our example, we'll use a slider joint. The constructor for slider joint takes the name of the joint, a parent body, and a child body. In this case, the slider joint will allow the body to slide along the ground's x-axis. A joint can provide between 0 and 6 degrees of freedom, and a joint provides a coordinate object for each of these degrees of freedom. The coordinate object allows you to configure a degree of freedom by specifying a name, a default value, and whether the coordinate is locked to a given value. The slider joint class provides just one coordinate, translation along the mutual x-axis of the parent and child bodies. Here we just set the name of that coordinate to be translation. Then we add the joint to the model. So we've finished adding a body and a joint to our model. To get the body to move, we need to actuate the model. OpenSim provides a suite of force elements, including passive elements such as ligaments. Active force elements are called actuators and are a type of force. Actuators are a function of a control signal. The point actuator class applies a force to a point. Coordinate actuator applies a generalized force, and OpenSim's muscle classes derive from the actuator base class. We'll add the simplest type of actuator, a coordinate actuator. This provides a moment for rotational degrees of freedom and linear forces for translational degrees of freedom. The constructor for a coordinate actuator takes the name of the coordinate to actuate, which, if you recall from the previous slide, we named our coordinate translation. Next, we set the name of the coordinate actuator itself to actuator, and we add it to the model using addForce. Now, as is, this actuator won't actually apply forces to or moments to the model because we haven't provided it with a control signal. That brings us to the last component we'll add to the model, a prescribed controller. A prescribed controller provides a control signal as a function of time. OpenSim includes a few other controllers, such as reflexes. Actually, computed muscle control is implemented as a controller. We'll need to configure this controller to control our coordinate actuator. To discover how we do this, we'll use methodsView. MethodsView shows that the prescribed controller class has a function, addActuator. This function takes an actuator that we want the controller to control. Scrolling down, we see there's another function called prescribedControl for actuator. This function takes 2 arguments, a string and a function, but we don't know what these arguments mean. so we can go to Doxygen. On Doxygen, we can search for prescribed controller in the search bar on the top right. The first entry is the prescribed controller class itself. The next two entries are for constructors of this class. Clicking the first link for prescribed controller takes us to a page that lists all functions in this class. We're trying to better understand the function prescribed control for actuator. This page tells us that this function takes two arguments. Act name is the name of the actuator we want to control. Prescribed function is an OpenSim function object that provides the control signal as a function of time. Now that we have a better understanding of what this function does, we can go back to our code. We'll use the two functions that we just found with methods view. First, we add our coordinate actuator to the controller using add actuator. Then we prescribe a control signal for this actuator by providing the name of the actuator and a function for computing the control signal. For the function, we're using OpenSim's sine class, which gives a sinusoidal function. If we wanted, we could customize the sine function with an amplitude and frequency. But to keep things simple, we'll use the default constructor for the sine function, which uses default values for the amplitude and frequency. Lastly, we add the controller to our model. So we finished building our model. Now we can create an OSIM XML file that you may be more accustomed to. First, we need to call the function finalize connections. The components we added to the model depend on each other. For example, the joint depends on two body components. When you build a model, these connections between components are stored in memory, but not in a way that is preserved when writing the model to a file. To ensure the connections are preserved in the file, we first call finalize connections. After finalizing the model's connections, we print the model to an OSIM XML file using the print function on model. You can open pointmass.osim in your working directory. That's what I'm showing here on the right. So we built a complete OpenSim model in Matlab. Now we're ready to use the model. First, we'll simulate it. We want to visualize our simulation, so we'll enable the API Visualizer window. The API Visualizer is a 3D rendering window that can be controlled through the API. It's not part of the OpenSim GUI. Before we conduct a simulation, we call the function initSystem. InitSystem is a very important function. After you call this function, you're ready to simulate the model, and you're not supposed to modify the model anymore. It's important that if you want to visualize the model, that you invoke the setUseVisualizer function before initSystem. At the start of the webinar, I mentioned how building a model contains two steps. You can think of initSystem as conducting the second step of converting your conceptual model into a system of equations. InitSystem also causes each component to verify that the property values you provided are valid. For example, OpenSim now checks that each muscle's max isometric force property is non-negative. InitSystem returns the default state of the model. What is this state object? The two most important classes in OpenSim are the model and the state. The model represents the equations themselves and any constant quantities like the mass of a body or the optimal fiber length of a muscle. The state represents everything that is time varying. Functions that return quantities that depend on time will require that you provide a state. For example, getting the mass center position of the model requires passing in a state object. The state object is conceptually a lot simpler than the model. It's just a vector of numbers. This separation between model and state is essential to reducing bugs in OpenSim and designing an intuitive interface. One of the most important functions on the state object is getY, which returns a vector of all state variable values. I've shown the results of getY on the initial state, which provides the value of the generalized coordinate and generalized speed for our 1 degree of freedom model. Here, you can see that both the coordinate value and speed are 0 initially. Now that you know the difference between the model and the state, we're ready to simulate the model. And it should now make sense to you that what a simulation does is compute a sequence of state objects for a constant model. To conduct the simulation, we use the simulate function, which takes a model, an initial state of the system, and a final time. If you've used Matlab before, the simulate function is similar to ODE45. It conducts a numerical integration given a set of differential equations, here represented as the model. It also takes an initial condition and information about the time over which you want to simulate. The result of the simulation is the final state at the end of the simulation. Running this code causes a visualizer window to pop up, which shows the sphere we added to the body. If you hit enter, the sphere will move as a result of the force applied by the coordinate actuator. You can then hit escape to close the escape key to close the window. All right, so we were able to conduct a forward simulation. However, the simulation usually is not the end goal. You probably want to analyze your simulation. In this case, we'll obtain the final position of the point mass. Computing quantities from a simulation usually requires these 3 steps: finding the appropriate model component for the calculation you want, finding the function that performs your desired calculation, the function on the model component that performs your desired calculation, and determining what other quantities your desired calculation depends on. Most components have functions that let you access or compute quantities of interest from a state. If you want the value of a coordinate in a given state, you want the coordinate object. We still have our coordinate object from before, and it has a function getValue, which returns the value of the coordinate. The value of the coordinate is time-dependent. Accessing it requires passing in the state. Now, this operation is fairly simple. The coordinate value is just one of the state variables, so all the coordinate needs to do is fetch a single element from the state vector I showed you earlier. But only the coordinate component knows which element of the state vector is associated with that coordinate object. We may also want the mass center position. This is a model level quantity, so the function of interest is on the model, not on a coordinate or joint. Unlike the coordinate value, we cannot simply fetch the mass center position from the state vector. This function must first calculate the mass center position of each body in the system. Calculating the mass center of each body requires computing the transform between each body and the ground body. These transforms are reused in many calculations, so we would like to avoid recomputing them. It's for this reason that I snuck in this additional line of code, model.realizePosition final state. Now I'll explain why this line exists. The state object in OpenSim can be realized to different stages, as shown here. When we realize to the position stage, OpenSim calculates and saves, or caches, the kinematic transforms for each body. When we realize to the velocity stage, OpenSim calculates and caches body spatial velocities. By realizing to the acceleration stage, OpenSim performs forward dynamics and caches the resulting generalized accelerations. By caching these quantities, OpenSim can more efficiently compute the quantities you're interested in. A state realized to the position stage can be used to compute position-level quantities, such as the mass center position, without needing to recalculate any of the body transforms. A state realized to the velocity stage can be used to compute velocity-level quantities, such as the mass center velocity. A state realized to the acceleration stage can be used to compute joint reaction loads, which depend on generalized accelerations. If we change the value of a generalized coordinate, then all saved calculations related to the position stage or later stages are no longer valid. Therefore, changing the value of a generalized coordinate causes OpenSim to demote the stage back to the time stage, which causes the cache for the stage's position and later to be deleted. If we change the value of a generalized speed, then the stage is demoted to position. In that case, the saved body transforms are still valid because they don't depend on generalized speed. Here's our code for calculating mass center position again. Calling realizePosition causes OpenSim to calculate body transforms, which are needed when computing mass center position. Without the cache and its associated stages, we would need to recompute body transforms every time we wanted to compute mass center position, or in any other quantity that depends on body transforms. Although having to call realizePosition is a bit confusing, it's associated with big performance benefits. We'll also get one more quantity for fun, the joint reaction forces for the slider joint. Because this is a joint level quantity, the function is on the slider joint object, which we called joint earlier. Joint reaction loads depend on generalized accelerations, so we first realize to the acceleration stage, which computes and caches generalized accelerations. We then call calcReaction on parent expressed in ground, which uses the cached generalized accelerations. This calculation is provided by the joint class. Here is the output for the coordinate value, mass center position, and joint reaction load. The point mass moves 0.5 meters from the origin. That's reflected in the coordinate value and the mass center position. The third row is the reaction force as a spatial vector. The spatial vector is ordered as mx, my, mz, fx, fy, fc. Let's work backwards to understand what these numbers mean. Fy, negative 9.8, is as expected. This is the force due to gravity. Fx is the force applied by the actuator, negative 0.997. Mz is the moment of the force of gravity about the origin of the system. So the distance, 0.5, times the force due to gravity, about negative 9.8, leads to negative 4.9. So now we've analyzed the simulation and learned how to use a state object to compute quantities of interest. Sometimes you're provided a model from somewhere else and you want to modify it. Next, I'll show how you can modify an existing model. We'll make two changes. First, we'll double the mass of the body, and then we'll increase the strength of the actuator. I've cleared our previous variables so that we can pretend we're starting fresh with a model that someone else has given us. Next, we load the model from an OpenSim XML file that we saved previously. I've stored the model in a variable named model. Even though I've used the same variable name as we used before, this is a different instance of the model because we cleared our previous variables. The change I want to make is to double the mass of the point mass. So we need to access the body object from within the model. To do this, you ask the model for the body set, then get the body by its name. The model class is a function UPDBodySet, which may sound familiar to you if you've opened an OpenSim XML file and seen a tag body set, as shown on the right. You might wonder what UPD in UPDBodySet means. When you use OpenSim, you'll come across functions that give you access to objects or components contained within the model, such as accessing the body set within the model. OpenSim permits two ways of accessing such objects: read-only, in which case the function starts with get, or read-write, in which case the function starts with UPD. Calling a UPD function has the side effect of requiring that you call init system again before you use the model, because the internal system may no longer be consistent with your model. We plan to edit the bodies in the body set by changing their mass properties, so we choose the function that starts with UPD. To get the current mass of the body, we call getMass. This function does not take any arguments. Notably, the mass of the body does not depend on the state. It's a property of the model itself. We then multiply this mass by 2 and call setMass on the body with this new mass. So now we've doubled the mass of this body. Next, we'll increase the strength of the coordinate actuator by a factor of 4. We use the model's function UPDForceSet and provide the name of the actuator. This returns an OpenSim force object. But the derived type of the force is still coordinate actuator. That's what we had added to the model originally. And we see the coordinate actuator in the inheritance diagram shown on the right. Now, the strength of the actuator is a property of the coordinate actuator class, not of the force base class, and so we cannot set the strength if we only have a force object. To convert the force into a coordinate actuator, we use the safe downcast function. When we call class on the actuator variable, we see that we now have a coordinate actuator. So that means we now have access to the functions for getting and setting the strength of the coordinate actuator. As a side note, you can also downcast to intermediate classes in this hierarchy. If we wanted to set the actuator's maximum control signal, we could have downcasted to scalar actuator instead. That class is also shown in the hierarchy on the right, because the maximum control signal is a property of scalar actuators. We're now ready to use this coordinate actuator. We obtain the strength of the actuator with the function getOptimalForce. We then multiply the strength by 4, then set the result to be the new optimal force of the actuator. To see the effect of doubling the mass and quadrupling the actuator strength, we can conduct a new forward simulation. Here, I printed the final position of the point mass with this new modified model. As we expect, the point mass travels 1 meter, which is twice as far as before. So now you've learned how to inspect and modify an existing OpenSim model. Now that you know how to perform these 4 tasks, you have a great foundation for automating your OpenSim workflows. How can you learn more? Here are 3 Matlab examples on OpenSim's documentation site. We have 2 examples related to a simple passive dynamic Walker model. The first is building this model from scratch. The second is simulating the model to walk as far as possible. The third example I'm showing here was just created by Nicholas Bianco and shows you how to write your own static optimization algorithm in Matlab. With your knowledge of the OpenSim API, you can go on to accomplish great things. Here are two large projects that OpenSim users have created. Brian Umberger used the OpenSim API in Matlab to create a direct collocation optimal control framework for simulating human and animal movement. Thomas Geitenbeek used the OpenSim API in C++ to create a predictive simulation framework. To continue your learning, you can use a variety of OpenSim's resources. There's the Doxygen API reference site, which I've shown you. There's the Confluence documentation site, which provides many guided examples. There's an Omni search bar on the OpenSim website that searches both Doxygen and Confluence. Lastly, you can view all of OpenSim source code on GitHub. I'd like to thank Joy Koo and Jen Hicks for all their help in preparing this webinar. In a moment, we'll take your questions. After that, the OpenSim development team will hold virtual office hours to help you work through the code I've just shown and to answer more detailed questions.
Thanks, Chris, for the great webinar. We'll go ahead and open up to questions. So if you have questions, find the Q&A panel, type your question there and send it, and we'll get to as many questions as we can in the open session. Chris, after this, do you have a slide or something with info to go to the Zoom room?
Yes.
Okay, so let's do general questions now. A couple people have asked if a recording will be available. Yes, you'll get as a registrant, you'll get a follow-up email that will have a link to the recording and other relevant links. Let me see, can I make this bigger? No, I can't. Okay, so a question from Josh Roth. If you want to change a parameter in the model after you invoke init system, oops, I'm losing my questions, then you make the changes and then repeat the call to init system?
Correct, yes. You can do a cycle of editing the model, calling init system, simulating it, then editing the model again, calling init system, simulating it. Just before you try to use the model, you must call init system if you've made any changes in the model itself.
Okay, we have a request if you could go back to the last slide.
Oh, the Q&A, this slide?
I'm not sure. So here, we'll show this for a second again. So find the Q&A panel in your WebEx and type the question there. And then, yeah, you could go back to the resources as well. And we'll send in that follow-up link. Can you go back one more slide?
We will show this slide at the end again.
Yeah, so you can.
I can leave this up.
Okay. Nobody will be there yet. We're still in the WebEx room, though. Okay, so let's see. A question from AD. So can one overload class functions? And maybe you could say a little bit more about what that means as well.
Yeah, I think what AD is referring to is changing the behavior of existing OpenSim classes. For example, we provide coordinate actuator, but maybe you want a version of the coordinate actuator that has specific behavior, maybe similar to the force length behavior of a muscle. To extend a coordinate actuator to have your specific behavior, you currently need to use C++. And in C++, you can create your own derived class of, in this example, coordinate actuator, and override existing functions in the class hierarchy. Unfortunately, right now, that ability is not possible directly in Matlab. But we also have examples of creating your own custom classes in C++, and we provide examples for that. Yeah.
Okay. So now a question from Emily Dooley. Can you make an actuator based off the current or real-time state, like position, velocity, not just the final state?
Yes, that's a great question. That is, there are two ways to accomplish that. One is if you have a passive force element, such as a ligament, that is just dependent. It's passive. There's no control signal. OpenSim already contains a ligament whose force is a function of the length of the ligament, and that's one way. But you could also have a muscle that is controlled by a controller whose control signal is dependent on the model's state. So we have an example controller in OpenSim that models a reflex where the control signal to a muscle is a function of the stretch and stretch velocity of a muscle.
Okay, thanks, Chris. Now a question from Jasmine Cruz. What would you say is the advantage or disadvantage to building a model in Matlab versus using an XML editor like Notepad++?
That's a really good question.
Mm-hmm.
It may be easier to get started in XML because the GUI has this nice window called the XML browser, and it makes it really easy to copy and paste a template for a component and paste that into a model XML file. But if you say wanted to make sweeping changes to your model, that's hard to do with XML editing. You might have to do a lot of find replace. I would personally use a Matlab script because, one, it's a little bit more readable. If you wanted to then pass your code to someone else, they can more concisely see how you built your model. It might also be easier to track changes that you've made to your model over time by like creating a diff between your MATLAB script over time.
Yeah, so I would agree that like small changes, oh, sorry, that's my cat. He apparently prefers the XML editor. For small changes, the XML editor, can be a quick and easy thing to do. Some of those changes you can even make in the GUI using the property editor. But making a lot of changes can be error prone and can be hard to find those errors. So in a lot of cases, either making edits in the GUI or doing them by MATLAB, like Chris was talking about, can be preferable. Great. So now a question from Dhruv Gupta. This is, thanks for the presentation. Can you talk about safe downcast again? I've seen that it's used very often, but I do not completely understand what it does. That's another great question.
Yeah, thanks for asking that. The need for safe downcast is partially due to a limitation in C++. This function UPD forset and the function get on the forset, in C++, since it's a statically typed language, this function has to return a force object. And just with C++, there's no way, since these functions are implemented in C++ originally, there's no way for this function call to return the true specific type of this actuator force. But as the person who created the model, you know that this actuator is actually a coordinate actuator. So this function does some internal tricks to take this force object and convert it into an object whose type is coordinate actuator. And it could be that you were wrong. Maybe in this case, force is a coordinate actuator, but maybe you tried to safe downcast the force into a point actuator. Maybe use point actuator.safedowncast. In that case, this function call would return null. It would return an empty object, indicating that you were wrong that in trying to safe downcast the force into a point actuator. I don't know if that's a fully satisfying answer, but hopefully that's a little bit more useful background.
Yeah, it's an intricacy of C++ and that OpenSim, the API is developed in. Mm-hmm. Yeah. Okay. So hopefully that helps, or if you want more discussion, we could try to talk about that in the Zoom room afterwards. A question from Jana or Jana Holder. Are there differences in using the API for OpenSim 3.3 or 4.1? What are your hints to update? So there are differences, and there's a release notes on Confluence, and then also some details, more details kind of from a development point on GitHub. So yeah, if you go to Confluence and see what's new with release such and such, there's a list there and history there, and also links back to the GitHub for more developer level information. Would you add anything to that, Chris?
When we released 4.0, we updated our entire suite of examples to work with 4.0, and so working from the new updated examples hopefully can help you.
Great, thanks. There was another question that I can't, here it is. So question from LR, does most of what you present also apply to the API in Python? I've found that not all classes are always available.
It's very likely that so we try very hard to make sure that the Matlab and Python interfaces are as similar as possible. There are some nice things in Python where, for example, we're actually able to remove the need in many cases for you to call safe downcast. So you might run into safe downcast a little less in Python. There's also a key function print. Let me pull up the correct slide. So I showed you earlier how you can print a model using the print function. Here. In Python, this would be print to XML. And we needed to make that change to the name of this function just because print is the name of a built-in function in Python. But if there's any class that's available in MATLAB and not in Python, that's a bug.
Yeah, and you can post if you could post a question about it on the forum or send us an email, or file a bug report or feature request too if you run into things like that. So a question from Yunus Revzanafar. Apologies if I've mispronounced that. Thanks for the great webinar, they say. Can the position of bony landmarks, for example, landmarks on the femur, be obtained using coding in MATLAB, C++, or Python?
Yes, and that's something that will be easier in 4.0 than in 3.3. As long as you have a marker component at the location of the bony landmark of interest in your model, then you can call a function. I think it might be like find location, and then you pass in a state object, and you get a vec3 of the position of that bony landmark in ground, expressed in ground.
Okay, thanks, Chris. Lots of questions coming in. We'll get to as many of them as we can, and if not, we'll either try to answer them in a Zoom session, or we can answer them by email later on. A question from Pedro Sarmet. So a question about the use of the analysis tool in OpenSim. When I use it to calculate active and passive forces, velocities, and powers of muscles and tendons, I don't know how to associate it with the static optimization force results. So I think that is an issue where with static optimization, you're not computing the full states of a muscle, or the states of the muscles throughout the simulation. You're just computing an activation and force. So you would probably need to do something like a computed muscle control simulation to use some of the follow-on analyses, like computing metabolic cost.
Yeah. Yeah, it's going to be easier to go from a computed muscle control solution because it produces a states file that is a storage file that has the value of all the states in the simulation, whereas static optimization gives you an activation file. So if you really wanted to use static activations, you'd have to do some like finagling with the data files to make the static optimization output look more like the CMC output.
Great, thanks, Chris. Another question, is it possible to perform inverse dynamics, static optimization, and all the other types of analyses, computations that you do in the GUI in Matlab?
Yeah, all the tools, scaling, inverse kinematics, inverse dynamics, RRA, CMC, analyze tool, those are all available in MATLAB and Python. And it's great to use those tools in MATLAB and Python as a way to automate your workflow to make sure that maybe if you make a change to your model, you can repeat your entire pipeline by just rerunning your scripts.
Okay, thanks, Chris. A question from Manta. Can you describe how to model the contact forces between two surfaces or show the references for how to do it?
Yeah, there's two model components, force elements. Let me go back to the graph of the different force elements in OpenSim. So it's not shown here, but one of the other functions of the motion, forces that are function of the motion, is Hunt-Crossley force and elastic foundation force. And both of those are compliant contact models that allow you to, for example, attach a contact sphere to the foot and attach a half space or a plane to the ground. And basically there are spring-like forces that are generated when the sphere penetrates the ground. And we have MATLAB examples for adding these to your model as part of the, I showed you, we have the passive dynamic walker MATLAB example. Here. So if you go to Confluence and you look for building a dynamic walker in MATLAB from the examples page, you'll have a great example for how to programmatically add Hunt-Crossley contact to a model. That's actually what these teal spheres are representing. These are contact spheres.
Okay, thanks, Chris. Let's see, a question from Samuel Gould. Is it possible to parameterize these sorts of models through MATLAB, for example, using a for loop to run several simulations passing through a number of different masses?
Yes, for sure. You can have a loop where you change the mass, do a simulation, then change the mass again. That reminds me of a study that some OpenSim researchers used a while ago to perform a Monte Carlo sensitivity analysis to observe which model parameters have the greatest effect, I think, on muscle activity. And I think they use the Matlab API to conduct that study.
A question from Logan Moore. Says, thank you for the great presentation. Can you elaborate on some of the most frequent error messages or common mistakes that you've encountered?
That's a good question.
Yeah.
I think, when people get started with the OpenSim API by just working off an example script, they often run into issues. And I think this presentation, we really focus on presenting some material that can really help you avoid those mistakes. So I think a common mistake, for example, is not calling init system before trying to use your model. And another common mistake is not calling realize position or realize dynamics or realize acceleration before you perform a quantity of interest. And so we've shown you and explained how to use those functions to avoid errors. Those are, I think, some of the most, those are two very common errors. Other common errors might be maybe someone edited an XML file by hand and then tried to load it into MATLAB through OpenSim, and they get an error related to perhaps they missed an angle bracket in the XML file. And you might be able to get more information about that. There might be web tools or other programs that can sanitize or check your XML file for syntax errors. And I would encourage you to use those tools if you get an error trying to load an XML file into Matlab. Yeah, one thing that might help, might be a reason to move to 4.0 is that we have continuously tried to improve the error messages to be more specific so that they can guide you through how to fix your error. That would be a benefit of moving to 4.0.
Yeah, another thing that can be helpful in general is kind of keeping things as simple as possible and then adding complexity. So, get a small piece running, then add more, rather than working with a giant model or doing the full optimization. So that can be a helpful approach as well.
Yes, that's great advice.
Okay, so we have time for a few more questions. We answered that one. So from Anahita Kashkai, thanks for the presentation. It was very informative. How can we learn more about the OpenSim API in Matlab or Python? Are there any specific resources or coding resources that you would suggest?
Yeah, so we have some examples on Confluence. There's also reading through the OpenSim forum on SimTK, you can see what problems people have run into in the past and what other projects there are. This webinar series is actually a fantastic way to learn about other projects. Maybe people don't advertise it, but maybe there's been some webinars that they're presenting their research results, but they actually use the OpenSim API internally. So referring to people's research projects that we advertise through our mailing list or through our webinar series, if you follow up with those resources, you might find that there's often a SimTK page backing those projects, and they might have resources there.
Great, thanks, Chris. Question from Pasha Ben Billard. Again, sorry for if I mispronounced, which I likely did. How sophisticated can you make your musculoskeletal model using scripting? For example, can you specify complicated muscle paths, insertions, origins? And if so, are there any example scripts available to learn from?
That's a great question. You can definitely specify muscle paths with the API. We have a very simple example of that on GitHub. There's a README example that shows you how to add a simple muscle with 2 path points. As for our Matlab scripts that create more complex muscle paths, I'm not sure of examples for that.
Yeah, I don't know those off the top of my head. You could try it with what Chris mentioned and then post a question on the forum if you're not able to figure it out otherwise. Then we could share, us or someone from the community could share a code snippet or two to help you out. Question from Sujata Kandare, is it possible to change the muscle model using the Matlab API?
That's a great question. What I've done most frequently, if I need to quickly change the muscle model, is I go into XML and do a find replace and replace, for example, failing 2003 with Millard 2012 equilibrium muscle. That's not really a great way to just change the muscle model because there are still differences that would miss. The names of some properties are different between the 2 muscle models. I would take great care when you try to replace the muscle model with. In the next release of OpenSim, we might have a utility to help people convert between existing popular OpenSim muscle models and the muscle model we use in Moco. Yeah, so you can definitely, for example, read what muscles are in a model and then create a new muscle and add that to your model based on the properties of the existing muscle. but it's a little bit more complicated than it might seem at first, but for a good reason, because these models are actually different, and you want to be careful when you make this kind of change.
Yeah, thanks, Chris. Oops, okay. Question from Lydia Bra. Is there a way to add contact forces like the ones from Hunt-Crossley foot-ground contact model to a reporter during a simulation? As far as I can tell, the only output available for those forces is potential energy.
That's a great question. We have not yet updated the contact models to use the new output system. So if you can still get forces. There's functions on the contact model, get record values, get record names, and that can give you the contact force values, and that's what we use.
Yeah, that's a good point or feature request we can add to the list, as well as to expose more outputs for the for those components in OpenSim. Okay, I think maybe we'll take one more question. Apologies again, we haven't been able to get to all of them, but I want to give time for everyone to navigate over to the Zoom room. So one more question. So a question that has come up from a couple users is whether it's possible to do real-time control using the API, for example, collecting data or sending data.
There have been some projects by people in the OpenSim community to do like real-time inverse kinematics. I think others might be able to speak more to that.
Yeah, it's possible. It's something that is definitely possible. It's not something that we have currently optimized the OpenSim API to do, but that's something that we're interested in and plan to do in the future. So it's possible now. If you search for real-time OpenSim, I think there's maybe a couple projects and papers already available. And again, we plan to do some more work in that arena in the coming development cycles here. Okay, so thank you everyone for the great questions so far. And thank you, Chris, for the awesome presentation. So I want to acknowledge our funding sources. So OpenSim development and research are supported by grants from the NIH, including the one that funds our National Center for Simulation and Rehab Research. Next slide. You can learn more about OpenSim at our website. The website includes information about the center, upcoming events, other resources for the OpenSim community. We also ask that you fill out the survey that will appear in a pop-up window at the closing of the webinar. And thank you again to everyone for participating. We hope to see you over in the Zoom breakout rooms, and we hope you will continue to stay involved with OpenSim.